Hi everyone, we're going to focus our work on simplifying radicals from now on, or doing arithmetic with radicals or solving radical equations. But for this section, definitely the simplifying part. And the idea here is if you have a radical, for example, a square root of a perfect square, you can just evaluate that and you're done. That's definitely simpler than leaving it written as a square root. If you have the cube root of a perfect cube, you should evaluate that. But we often run into square roots that don't have a perfect square underneath. And the question then becomes, is there anything we can do to make these a little bit simpler? And the answer is sort of yes. The idea here is going to be that less is more. So we want the smallest number possible under the square root. And there are things that we can do to move numbers into and out of square roots. We have to be thoughtful about it, but we can do it. So this really does boil back down to our property of square roots that says if you multiply root a times root b, you can combine those roots and you get the square root of a times b. And we can also use that in reverse, and that's what we'll be doing here. So our goal is going to be to extract any perfect squares out from under the square root. So we'll be looking for any factors under the square root that we can actually take the square root of. For this first example, we're working on 45. So if you can just spot the perfect squares there, remember, you can even jot them down off to the side. Those are 4, 9, 16, 25, 36, 49, etc. If you can spot that one of those is going to be a factor, you can go straight for it. If you're having any trouble with that at all, you can work on building the prime factorization of the thing under the square root. So in this case, either way, we're kind of going to get the same thing. I'm going to get 9 times 5 if I try and start factoring that number out. And you can pick, if you have multiple options there, we could have done 15 times 3. It doesn't matter. Just pick one and go with it. And then you'll look at each of those factors and decide, is it prime, in which case you're done, or is it composite, in which case you want to split it up more. So here we have a 3 times 3 times 5. Anytime you get a factor that appears more than once, that's a perfect square and you're going to be able to extract that out. So we want to split this up and say, okay, well, this is the same as the square root of 9 times the square root of 5. And that's just back to this square root property up there. If 45 is 9 times 5, then the square root of 45 can be split up into the square root of 9 times the square root of 5. And we know the square root of 9 is 3. Which means we'll end up with 3 root 5 for this one. So you're looking for anywhere where you have that repeated factor, and basically moving that factor out in front of the square root eliminates one of your repeats, right? We had it squared and now we've taken the square root, so there's only a single 3 left over to put out in front. Okay, let's try it again with 72. So again, if you can just work your way down this list and spot a factor that you think is going to work, bigger is better. For this one, if you're looking and you're good at spotting these, you might see that 36 would work. If you've got that, just go for it and start splitting your square root up. But if you're getting stuck, we can go ahead and we can start dividing this out. We could do 9 times 8. If that's the first factorization that you spot. And we can break down the 9 into a 3 times 3. We can break down the 8 into, for example, a 2 times 4. And then we can even go one step further this time. We can say 3 times 3 times 2 times 2 times 2. And again, you're going to take out any pairs that you find. So if you want to, you can put that back together. That is that 36 that I spotted before. But you can also keep them separate. You could say, okay, well, I'm going to split this up into the square root of 9 times the square root of 4 times the square root of 2. And you don't have to rearrange the order, but my habit is to always keep that lonely one and just write it last, because the final version of this, we do want that square root written last. I can go ahead and evaluate the square root of 9, that's 3. The square root of 4 is 2, and that square root of 2 I'm stuck with, so I'll just rewrite it. And my final answer will be a 6 root 2 for that one. So notice, if I had just stuck with that 36 I spotted at the beginning, I could say 72 is 36 times 2. So I can split it into the square root of 36 times the square root of 2. Square root of 36 is 6. So we get to that same answer, 6 root 2. So if you can spot a bigger factor, it will give you a little less writing and a fewer number of steps that you have to work through, but you're going to get the same answer. So do whatever you're comfortable with, and you should work through those fine. Okay, so let's step it up just a little bit. What if we have variables under the root? And this is actually trickier than you might think, because x to the 5th, we have an exponent now, and we're trying to take the square root, and you have to think about that a little differently than just factoring a number. So I can start with 12, and what I'm spotting there is that it's a 4 times 3, which we can think of as a 2 times 2 times 3. So we're going to want to extract one of those 2's out. So we can rewrite that as a square root of 4, and we're going to have a square root of 3 left over. But let me leave a little bit of room in the middle for the x's. So the idea with x's is actually exactly the same. You don't have to write them all out every time, but if I write that out, I'm looking for anywhere that I have a pair of factors. So I should be able to extract out an x squared and then another x squared. So this is going to be a root x squared and a root x squared, and there's going to be a single x left over with my 3. So I'll just add that into that last root. I don't need to separate those. I just make that last root the home of anything that I can't simplify more. And when I break that down, the square root of 4 is 2, the square root of x squared is x, and then we have a repeat of that, so we'll have another x times the square root of 3x. And I can do just a little bit better with that. I can make that a 2x squared times the square root of 3x, and that will be my final answer this time. So with the variables, it is the same process, but it looks a little bit different maybe. Basically, what we want to do is pick out an even number of x's. So we want to separate off x to the 4th and leave that single x out. Okay, let's do one more square root, this time with 2 variables so we can really think about it. I will start with the 125, which looks divisible by 5 for sure, so I'll start with that. And it in fact ends up being 25 times 5. If you need to double check your arithmetic by doing some division there, go for it. Check 125 times 5 to help you factor. Try to not use the technology to actually pick out the perfect squares for you. And I'm actually going to leave it there because there's my perfect square that I want to separate out, and there will be a single 5 left over. Again, with the a to the 8, you don't have to write this out every time. Sometimes you're going to have too many, but as you're trying to figure out what's going on, you can think about this as I'll have 4 pairs of a's. Barely going to fit in there. So I get to extract out all of that. With the b's, I'm going to have 5 pairs that I can separate out and 1 b left over. So since I don't have room to write that all out, I'm just going to split that up into b to the 10 times b to the 1. So when I write this out, I'm splitting off a square root of 25, and I'm splitting off a square root of the entire a to the 8th, and I'm splitting off a b to the 10th, and I'm left with a 5 and a b. So the square root of 25 I can do, that's 5. This is where, as you practice, you'll feel a little bit more comfortable, hopefully. The a to the 8th, remember that a square root is a 1/2 power. So if you're up at the exponent level, you have an exponent in the mix, you're actually just dividing that exponent by 2. So a to the 8th to the 1/2 becomes a to the 4th. Similarly with the b's, b to the 10th to the 1/2 becomes b to the 5th. And then we can't do any better with the 5 or the lone b, so we will leave that under the square root. And that is as simplified as we can get this. And this might seem a little bit crazy, but it does actually become really useful at certain points as you move on with math to be able to move things in and out of the square root. So while I don't really care that every radical that shows up is in a fully simplified form, I do care that you can do this split radicals up stuff and the combine radicals back together stuff. Those are both really important skills. Okay, let's go ahead and work on a couple of cube roots. I don't want to get too tangled in this, and I don't want you to have to deal with anything too messy, but I do want you to be able to think through the process here. This will be a little bit different. If we're trying to take a cube root, we need 3 of the same factor for this to work. So I will start the same way. I'll say 24 is 6 times 4, for example. You pick your factors to start with. I can break that down a little bit more into 3 times 2, and I can break the 4 down into 2 times 2. And maybe you can see there, or maybe you could have seen already in the last step, that I do get 3 2s. So I'm not going to be able to take the cube root of 3. It's not a perfect cube, but I can take the cube root of 8. So I'll split that up into a cube root of 8 times a cube root of 3, and that becomes 2 cube root 3. So same idea, but this time we have to remove groups of 3 of the same factor. Let's try the cube root of 54x to the 5th. So 54 will approach similarly. That's a 9 times 6. And 9 I can break down into 3 times 3. And 6 I can break down into 3 times 2. And it's kind of the reverse of last time. Again, if you can just spot, you could list your perfect cube. So 2 cubed is 8, 3 cubed is 27, 4 cubed is 64. That's probably as big as you'll have to find in these. So if you can spot one of those right away, if you see that there's a factor of 27, you can jump straight to that. But if you're having any trouble, just break it down and look for those triples. Let's do the x's as well. X to the 5th isn't so big that I can't write it all out. So I'm imagining this, and I want to separate off the group of 3, so I'll have 2 x's left over and a single 2. So this will look like the cube root of 27 separated off, the cube root of x cubed is separated off, and the cube root of 2x squared is going to be left over. The cube root of 27 is going to be that single 3. Again, that's why we're looking for the triple. We're looking for 3 of the same thing, and when we take the cube root, that will only leave us with 1 of those. The cube root of x cubed, those are inverse operations, so that should just give me an x. If I cube root a perfect cube, I should just get back whatever I started with. And I'm stuck with the cube root of 2x squared, so I leave it just like that. And again, this might feel funny. I don't necessarily think that looks simpler when I started with. I have more mess. But the goal is just to play with removing things from square roots or putting things back into square roots. All right, just one more. So let's go for it. This time we have 2 variables to think about, and the powers are a little bigger. So 64 actually is a perfect cube, right? So if you spot that right away, you can just separate that off. If you don't, you can start splitting it up. 64 is 32 times 2 is a good example. If in doubt and you got an even number, divide it by 2. 32 is 16 times 2. 16 is 8 times 2. Remember to keep track here. It's 8 times 2. Okay, and then I still got my 2 2s. 8 is 4 times 2. And then how many do we have? 1, 2, 3. And then 4 is 2 times 2. And then 1, 2, 3, 4. So this time, if you do it out longhand, you can see you get 2 groups of 3. So we can factor out a cube root of 8 and another cube root of 8. Again, if you see that the cube root of 64 is going to be nice right away, that's going to be 4, do it, you're done. But I want to keep showing this process for people who don't spot them because that's a much bigger issue. Okay, so the x to the 10, remember we're looking for groups of 3, so I'm going to quit writing them all out longhand since this is a little bigger, but I'm going to say I can split off an x cubed and another x cubed and another x cubed. That would be 9 x's written out, and there will be a single x left over, so I can split out all of those. I'm going to run out of room up above. For the y's, I can split out all of them basically, right? I can do a y cubed times a y cubed, that's 6y's. That's 9y's, that's 12y's. So I can split out 4 of them, which means I'm not going to write it all out. So I have the cube root of 8. Now let's see, we'll sneak it over here. So I have 2 times 2, and then I have a cube root of x cubed, which is an x, another cube root of x cubed, which would be an x squared, and another cube root of x cubed, which would be 3 of those. That will give me 3 x's. And then for the y's, I'll have a cube root of y cubed is a single y, another single y, another single y, another single y. So y to the 4th is what's left over. Or again, you can think about that as y to the 12 to the 1/3, and 12 times 1/3 is 4. And then we're left with the cube root of, what's left over? Just an x is the only thing left over. So let me write that a little bit nicer. 4x cubed y to the 4th times the cube root of x. So they can get a little messy, but just keep looking for those factors that you can actually remove from the radical, and that should get you there. Thanks for watching.